Thank you. Thank you so much. I would like to thank the organizers to accept our proposal and giving us a chance to be here. Before we go into the problem, we've been doing this, as in Cubit has been doing this, I think, from the very first AQC we had. Most of the audience actually knows us, but for those who don't, just a one-slide introduction. So what Cubit does is exactly what we feel about the problems in general, which is we feel that the optimization problems or other hard problems, they do not or aren't necessarily wedded to a particular hardware. And we believe, or I at least believe, that Cubit isn't either. Around 80% of the logos on the right side, we have some kind of an arrangement and good partnership to actually access their machine and solve different problems. For the rest, we are trying. Now regarding today's talk, so it can be divided into these 4 parts. And the reason we chose big data visualization is because this came out as one of the problems that we actually faced when we had a particular client who gave us a lot of data. So the motivation is, you might have heard this many times, that the data that industries have these days, it's growing so fast, and 90% of the data that exists today has actually been produced in the past 2 years. So the point is, everybody wants to use the data. They want to make decisions that are data-driven. They want to predict what a consumer or customer might do, where the fallacies might come. But sometimes it's not easy to actually ask the right question from the data. For example, this might look like a very nice abstract painting, but when I tell you that this is actually flights from one city to the other, now that you visualized it, you would have interesting questions in your mind. But visualization is not always easy. For example, with a lot of data, sometimes your screen just sees a clutter. And especially for point cloud data, this happens a lot. So one way to actually look at it is if somehow you could club similar points together, so abstract some meaning, maybe you can call it coarsen it. So there's actually a field now that actually deals with this. So this is an example of what you might be able to do if you are able to abstract this thing and coarsen and cluster these points. So let's say this is the data set that you have in hand. This particular one is from a bank, Portuguese bank, and all these points actually show an individual customer. And if you really want to analyze the behavior and want to see why they took certain decisions which were different from each other, maybe if you could cluster them well, then you could do some kind of analysis by choosing the particular cluster, looking at different features. And this is the motivation behind this work. So what is the problem at hand? The problem at hand is basically a data analysis problem. You can call it a coarsening or a clustering problem. Everybody knows what clustering is. You have to basically find similar data points, and you need to club them together. But how this is different from what the industry has been doing till now is that you are not necessarily looking to bring down 1 million or even more points to 10 or 20 clusters. What you're really trying to do is slowly go down. And so for something like 1 million to, let's say, 100,000, and if you see an interesting pattern, you want to analyze it there. If not, then you go further down. So this particular clustering, where the number of clusters is also very high, is called extreme clustering. And of course, it falls under unsupervised learning. So what's the method here? So for demonstration purposes, we do not have 1 million points, but a certain number of points. Let's say this is the data set that you have. Now, it's very intuitive to see that when you want to cluster these or coarsen these and find similarities and club them together, you can safely say that somewhere, some point here has nothing to do with this point here. So this was the motivation, and that's what we wanted to do, that can we actually decompose this problem into independent chunks and then do some kind of processing on those chunks. So rather than having equal-sized decomposition, the simple algorithm that we came up with is if you find a median on the x-axis, so you basically now have equal number of points on the left and the right. Now you have these two independent chunks, and now you divide it maybe on the y-axis, again, equal number of points, and you keep on doing that. So this is, of course, on a 2D plane, but visualization can also be on 3D, so you can do the same on 3D. Of course, it won't look like what it's looking as in uniform cubes, but I couldn't get a better picture. So once you have these chunks, there are different ways you can process them. Of course, the traditional serial way, or if you have number of processors, you can actually go the parallel or the distributed way. So once you have chunks, now we want to do some kind of processing on these chunks. And the processing you want to do is somewhat like this. If you were able to find certain points within a chunk that have certain similarity or the radius of influence such that they cover all the points in that particular chunk. So I go back again. So this was your original. If you could find these yellow points such that defined with a defined radius of influence, they could cover all the other points. So to do this, we have a classical heuristic that we came up with, but we also have a QUBO-based approach, and that's the one I'll discuss here today, because that's where our quantum annealers and other processors come in. So it can be looked at as a simple minimum set cover problem. Everybody knows, but I show a very trivial example here. You have a universe, you have 3 sets with different members from that universe, and your job is basically to find the minimum number of sets that basically when you take the union, it covers the whole universe. So that's how you can define different ways that you can define a minimum set cover problem. This is one way where it's easy to comprehend what's happening. So you have a binary decision variable xij, where it's 1 if element j is covered by set I. Then yi is a decision variable. It's 1 if you actually chose that as belonging to the minimum set cover. And cij is an input variable, which basically defines whether the element belongs to the set J or not. Not necessarily covered in the solution, but actually it belongs or not. So if you could minimize this, and if you could do this well, you should get those points. So coming back, once you've done this, you can see this as normal clustering, what happens in the normal clustering algorithms. Now going forward, rather than remember, this is just one chunk that we are processing, and you would do this for all the chunks. Going forward, you can collapse them, and you can collapse them. Basically, if you're looking at a 2D plane, you can take a weighted average of their XY coordinates. So if you collapse them like this, you started from here, you collapse them, you had different chunks, you did for each of them, and now you bring it together to again have one big start. So now, depending on what radius you chose, depending on how many points you actually want in your final visualization, you might actually stop here, or you might go further. So this is how the pipeline looks like. You have the original data set, then you get the chunking module, then you have different chunks. Depending on whether you have more number of processors or not, you get these individual processed chunks, the compressed chunks. Then you combine them, and then you see whether you're done or not. If not, you go back and you do chunking again. So how did the results look? Seems all good. We actually went and picked up a data set that's used a lot in benchmarking clustering algorithms. So this is an MNIST data set, handwritten digits. And we don't have all the points here, which is the data set actually has 70,000 points, but we chose 5,000 points. Now, the results we have here are from the D-Wave 2000Q machine. We are actually comparing it with one of the well-known clustering algorithms, which is k-means. And we were actually surprised when it actually did so well in the scoring. And this is the score that's traditionally used to see what kind of clustering happened. It's defined as the ratio between within cluster dispersion and the between cluster dispersion. So we should actually stop here and think again. What we've actually done is picked up way high number of points that can actually fit onto a D-Wave machine. But we've been able to do clustering in a fashion that is comparable with the currently known best algorithms. So not all credit goes to D-Wave, of course, because the algorithm which is very simple, but the way it divides, it seems that it divides it in a way that you don't lose much information. And of course, D-Wave gave us the right solutions to the minimum set cover problem. Then we actually looked at another data set that clustering algorithms use a lot to benchmark. It's a synthetic grid with a certain mean and variance. Every kind of group here has 40 points, and we have 64 such groups. And this is the end coarsening that looks like. So yeah, D-Wave does do well. So this is an important slide. The reason I wanted to show here was this is not D-Wave result. So this is our heuristic result. But what we are comparing it with is the currently known state-of-the-art clustering algorithm, which is both in quality and time, which is known as Birch. So using our heuristic, if you are coming down from 1 million points to something like 0.8, 0.6, 0.4, 0.2, that algorithm cannot even comprehend doing that. And both of these comparisons are on this very laptop that I'm using to present. So it's a fair apple-to-apple comparison. So what this actually tells us is, and the reason why we didn't do D-Wave comparison here is because D-Wave can only take so many points in a chunk. So if we had to divide the 1 million point data set into so many chunks, we would basically be using D-Wave for days and days. And D-Wave bills us a lot these days. So what I really want to show here is that if we can have a limited size device that has certain characteristics, then maybe actually using it to perform certain real-world applications is not that far away. So what are the characteristics that are needed for this particular problem? One would be that maybe there shouldn't be much embedding time, because embedding would slow it down. So you would have different set cover problem that you are solving in each chunk. So if you don't need embedding, maybe you should have a good connectivity. So here, maybe Fujitsu's processor might actually do better than D-Wave. Other characteristics can be that if you have more than one device, then you don't have to wait for each chunk to be processed before the next chunk goes in. If you have multiple devices, you can do this in parallel, and certain other characteristics. But what I wanted to show was exactly what I said earlier, that given certain characteristics, we might be able to come up with decomposition techniques which suit particular problems, not necessarily in general, and might be able to solve problems that actually matter to the real world today. So we've submitted our paper to NIPS, so that's why I couldn't put it on archive, because they have certain restrictions, because they want to keep papers anonymous. We get the result by July end. If it don't get accepted, I'll put it on archive. If it do, I still put it on archive. Then we have ongoing discussions with clients. And an important extension to this is that for visualization, you only need 2D and 3D data sets, but we are trying to extend this algorithm to n-dimensional so that we can actually do any kind of clustering, not just on visualization side. Another thing that we are really up to these days is doing Fujitsu benchmarking on it. I think we'll be able to add that to our paper as well. And if you really want to go ahead and look at certain data sets, that this tool works with, you can go to this website, and we have 3 real-world data sets that it works on. One is from banking, automobile manufacturing defects. This is the team that actually worked on this, so I'm really thankful to them, including researchers and software developers. And one benefit that you get from being with a company for long is you get nice alias emails. So this is an easiest email ID that you could remember. If you have any question, please. Thank you.
Thank you.
Hi, so I had a question about the Ames data set that you used. So you have instances there of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I wanted to know, were they balanced clusters, like you had just as many examples of each of those? And my question would be, how well would this perform if you had clusters of different sizes? If you had a very imbalanced data set where you have a large cluster and a small cluster? Because it looks like you're partitioning on the median, and I'm feeling like you're not going to capture those clusters that well there.
You're right. This might have certain drawbacks, which many other clustering algorithms also have. So when there's a really imbalanced data set, somehow it starts to fall into anomaly detection or outlier detection. It might not do great in that sense. That's why we do not call it a clustering algorithm. We still want to call it a coarsening algorithm, which would be more useful on the data analysis side when you're going from high number of points to low stage by stage, rather than really at the end when somebody could tell you these are the outliers. So you're right. Just like certain other algorithms, it might have certain deficiencies. Just to let you know that the Birch result that I showed, where we were completely outplaying it in terms of time, the quality that we got was exactly what Birch got. So again, if it had certain deficiencies, we had the same.
All right. Yeah, I think your last sentence was an answer to this question. I was going to ask you about whether any analysis was done on the quality of the clusters that you showed in the third to last slide.
Yeah, that's
exactly what you just said.
Yeah,
so.
it was exactly the same.
Yeah.
Because Birch can be tuned to get different quality if you want to take less or more time. So we matched the quality to get that time.
Great. Let's thank the speaker again.